if you are following in sector then, what you'll see is we're actually not quite up to where we're supposed to be. So if you go back a few lessons, I'm just using that little star here. That's where we're up to in the lessons, okay? So we're actually up to the first little section, and if you're referring into the lessons, it's solutions and ionic substances, which is 4.2. So we are jumping around a little bit, but because we just did secondary bonding, it makes sense, and hopefully by the lesson it will be making more sense then, even more. All right, now, so the first thing we need to have at our disposal really is our data sheet. And the reason we need the data sheet, and you take this to every lesson and it's part of your chemistry bundle, is it's got the solubility table on it. And I'm not sure whether you've been through that before with anyone, okay, at year 10, but solubility table is critical because the solubility table tells me which salts are soluble and which salts are insoluble, which means, what does insoluble mean, Jameson? Can't be dissolved. Excellent. All right. So if I said, for example, calcium carbonate is insoluble, if I took some chalk and put it into a test tube with some water and shook it like crazy, wouldn't matter how much I shook it, how much I heated it, it's always going to have a precipitate in the bottom of the test tube. So we call that insoluble. So anything where we have a test tube scenario like this, and I've got a solvent, and the solvent that we tend to use is always water, where we're getting solid in the bottom, we call that a precipitate. And that implies that a chemical is insoluble. Now, again, what does it mean it's insoluble? Who remembers what sort of bonding we're talking about when we're dissolving something like salt into water? Do you remember what sort of bonding we spoke about? Not ionic, Luke? Ion dipole was what we referred to, okay? And so we said that if this is our lattice, this is our ionic lattice, and this is our solvent, which is water, we said that this is a polar molecule, and we said that this is the delta positive of the structure, this is the delta negative. And we said the delta negative, Maddie, you should be watching, the delta negative will go towards the the Na plus in the lattice. Okay, and the delta positive, which is the hydrogen, they will go towards the chloride ions in the lattice because opposite charges attract. So we said that this is just another form of H bonding, another form of secondary bonding, I should say. So we've done H bonding, dipole-dipole dispersion, and now we've got ion dipole. Now, in your books, there's a really good diagram, and I had it on the board last week. And so in terms of dissociation, it would look something like this. So if I were to look at a straight sodium ion that would have been connected to a chloride ion in an ionic lattice, and we know that that lattice continues. If I add water to that, we all have to obviously understand that it's soluble, and the water being a polar solvent, and we'll do it as a polar, negative, positive delta, we'll eventually end up with this scenario. So we've got a sodium ion, and we've got a chloride ion, and this should obviously be in a beaker. It doesn't happen in space, but all right, I haven't actually drawn a container, but imagine this is happening in a container or in a test tube. All right, it's not a gaseous system as such. And so inside of our beaker, what we find is that the oxygen of the water will orientate itself just like this, and it will form an ion dipole bond with the sodium. And it will do it again. Up there, delta negative, delta positive, dot, 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 another ion dipole. So the water will orientate delta negative to positive for a sodium ion. Now for the chloride ion, it does the opposite. The molecule can move. That's my delta negative. This is my positive delta here. And so I'm going to get an ion dipole bond around the chloride. Same thing here. The water's going to reorientate there. That will be my delta negative. This is my delta positive, and I'm going to get another ion dipole there. So that's actually what happens on a molecular or on an atomic versus molecular scale. Alex, question it.
So there has to, so for it to dissolve completely,
yep,
that means there has to be enough water, so enough H2O to bond with all of the Na and Cl.
Excellent, good question. All right. So if I had salt, for example, sitting in a test tube, and I wanted to dissolve the salt, if I add 1 drop of water, it's not going to work. If I add 2 drops of water, it's not going to work. I need to have enough water molecules to completely surround all of those ions. Remember we spoke about a saturated solution last week as well?
Yeah.
So I could do the opposite. I could have water, add sodium chloride, add sodium chloride, add sodium chloride, keep on going, stir, keep on going, and eventually it will become super saturated. Means I've got an actual solid at the bottom, and that's not a true precipitate because sodium chloride is soluble. But I simply have added too much salt for the water to get around the ions. Does it make any sense? I'm cool with that? All right. So really what we're doing then, if you imagine what's actually happening, if this is just sodium chloride, solid, and if I want to break these bonds apart, how would I do it? In the lab, how would I do it? Heat, exactly. So I would need to heat this to what temperature? Melting point, because it's a solid. Okay. But the sodium chloride's got a melting point of over 600 degrees Celsius. So I can only just do it with the Bunsen burner. Only just. So I'm breaking these bonds. But if I put sodium chloride at room temperature into water, it just melts apart. It's not really melting. It's the ion dipole that's doing all the work for me. I don't need to add any heat to water to dissolve the sodium chloride.
Does it help?
It does help, Alex, yes. If I were to heat the water up, that means I can dissolve more sodium chloride in here, okay, if I wanted to, and make it more saturated. However, the whole idea is, as soon as I actually take a salt that's soluble, put it into a polar solvent, in this case water, ion dipole does all the work for me. It automatically breaks down the lattice, okay? So all these ions just start to dissolve, or they become what we call solvated, okay, into the water using those ion dipole bonds. So that's what we're doing when we actually dissolve a soluble salt into water. The equation. Now how we draw this. Now I've given you a different sort of image on the board there. So we actually don't draw it like that. We actually do it like this. So I'll give you the ionic equation for this. So it looks like NaCl solid, and we have to be specific about S for solid. So we start to use solid, liquid and gas now. Okay, so we're going to use all three. So we now add AQ, and AQ is aqueous, which means water. So most of this we're actually adding water, and we end up with Na plus AQ, which means Na plus surrounded by water molecules plus Cl minus AQ, which is chloride ions surrounded by water molecules. We call those solvated, okay? Soluble salts, okay? It's called solvation, but we're going to use the word dissociation in this instance. Alex?
So you write them separately because they become separated, and that's why it dissolves?
Yeah, that's right. That's why we do it separately. We want to show them individually separated. Now you will also see in books this done as another equation. You might see it like this. You will see it written down as NaH2O 6 plus. Okay, Okay? At stage 2, you'll see it like that. Any questions? Why 6?
Yeah, why 6?
Any ideas?
Because of the overseas nitrogen.
It's just to do with the size of the ion. That just happens to be that 6 is the number that fits around the ion. Okay? Every single time, it's a magic number. For things like copper, we can only fit 4 water molecules around copper because of the size of the ion. But for most ions, 6 is common. That's actually how many water molecules we have around the outside of the ion when we dissolve it into water. Alex?
So how was that number determined then?
By the size of the ion.
Yeah, I know, but what do you mean by that?
Well, obviously what we can do is we can measure the moles of the sodium. We can weigh out sodium by mass, can't we? So you can work out the moles of sodium.
Yep.
You can add a specific volume and mass of water. You can work out the mole ratio of 1 is to 6 for every individual ion. That's how they do it.
Okay, so you need 6 moles of water to dissolve.
Yeah, you asked me that question at the beginning, all right? So how much water would I need to add? Well, approximately, given that they're not the same molecular weight, but if I had sodium chloride, if I had 1 gram of sodium chloride, for example, sort of approximately, I'd need to have at least 6 grams of water to dissolve 1 gram of sodium chloride. Well, actually not 6, I need 12. Because I've got to count the chloride ions and sodium ions. Now that's not a very scientific way of doing it, but that's how you would work out it's actually 6 is the number. That's the magic number. Okay, everyone happy with that? I'm recording this just for you. Okay, all right. Precipitation reactions. Oh, while we're on that, dissociation reactions. Now, if we go to our solubility table, okay, so we look at things like carbonates, all insoluble. All carbonates are insoluble, except for sodium, potassium, and ammonium. So if I were to do a carbonate idea, and if I asked you to do some equation, let's say for calcium carbonate, it would look like this. You would say calcium carbonate, solid, plus AQ gives, it's insoluble, so how are you going to show me that it's insoluble? It doesn't dissolve. So I start off with a solid, I add water, I end up with a solid. Okay? So in case you were wondering how we do an insoluble equation, that's how we're going to look at doing an insoluble equation. All right, questions? Everyone happy with that? All right, next one. All right. The next thing we want to look at is a precipitation reaction. And a precipitation reaction goes something like this. It has a soluble salt mixed with another soluble salt, and it will normally form an insoluble salt, plus a soluble salt. And I'll use an example, okay, for this as well, and then I'll rewrite that for you in a minute. All right, so a soluble salt. Here's an example that we use to test the chloride in water. Did we do this earlier in the year? Did I ask you to test for chloride in water?
Yeah, you add something to the water.
Yeah, okay, so we used a test earlier on in the year, and I said if the water contained salt, then I was going to add something to it. And if you remember, I think we were going to add silver nitrate, correct? Okay? Yep, silver nitrate. And we were actually testing for the presence of chloride ion. And really what I was asking was, is there any salt in the water sample that we had? This is an actual practical application. And if you know which salts give precipitates, you can do a whole series of tests and you can narrow it down to what ions are in the sample that you're given. Okay? Qualitatively. The same thing, we could do the same thing with fluorine. Yeah. All right. So I just wanted to test: is there any chloride in water? Now I have to work backwards because I have to find a precipitate that's got chlorine in it. Go to our periodic table. Chlorides, all soluble except silver, lead, and mercury. Silver, lead, and mercury, all soluble. Sorry, all of them are soluble except for those three. Soluble. So what does that mean about silver? That means silver chloride's insoluble, mercury chloride is insoluble, and lead chloride is insoluble. So how do we put it into an equation? I'm pleased you asked. Soluble salt, well, we use silver nitrate. So we put down silver nitrate, aqueous, okay? Because it's dissolved, it's an aqueous solution. You are provided with silver nitrate. How do I know it's soluble? Because all nitrates are soluble. It's just a solution that we used, and you were given that to test chloride. Now, if we ended up with sodium chloride, if it was in the unknown, okay, then we would end up with the following. Now, you have to then go back to your solubility table and think of what you've actually got in this solution. So if I've got two soluble salts in a solution, we've actually got this. So if this was what I'm doing, I would end up with this. It's telling me that I've got Ag plus here, aqueous. That's free in solution, yeah? I'm also going to have nitrate ions, NO3 minus, aqueous. They're going to be in solution because it's soluble. I'm going to have sodium ions because I already know that sodium chloride's soluble. And I'm going to get chloride ions as well. All these will be aqueous. Now, which ions do you think are going to bump into which ions? Any ideas? Alex?
The silver will be attracted to the chloride.
Good. So this is going to happen. Yep.
And then, well, it wouldn't really matter though, because there's two negatives and two positives. Couldn't there?
Yep.
Yeah. Go that one.
So if it goes to silver nitrate, what's it going to do? If a silver ion bumps into a nitrate ion, what's it going to do?
Silver is going to bond.
Is it? Silver nitrate's soluble. It's just going to actually unbond. Silver nitrate's soluble. So it's just going to go back to silver nitrate in solution. The sodium ion will dissociate and the nitrate ion will come apart as well. Does nothing, in other words. With those two bumped together, nothing happens because they're dissolved. They're soluble. They eat one another, dissolve, dissolve. We only get a successful if these two come together. Why? What about sodium and chloride? Can they come together?
Yeah.
Yeah. What happens when they bump together? Same thing. They're going to separate. They're going to redissolve again because sodium ions and chloride ions are soluble. Here they are. They're aqueous. What about if the sodium and the nitrate come together?
There's water in there as well.
Yeah, there's water in there.
Yeah.
What about if sodium and nitrate come together? What do you know about all sodium salts? All sodium salts are soluble. So what's going to happen with that? It will dissolve again.
Yeah.
There's only one possible outcome. And the only outcome is, just so happens, that whenever a silver bumps into a chloride, I'm going to get a precipitate. And we can use this because we happen to know, maybe you don't, but the actual precipitate, silver chloride, is white in colour.
Yeah,
it's white. And some of you saw that because it turned cloudy. And the more whiter the solution, the more white precipitate that you get tells me how much sodium chloride is in the sample that's not supposed to have salt in it. Okay? Alex?
So the natural that we get given to drink through our taps, does that have sodium chloride in it?
Well, obviously it does. It's got some chloride. We don't know whether it's sodium chloride. We just know it's chloride.
Yeah.
Okay? But we made the assumption that it's probably salt. Comes from Murray.
Yeah.
and Murray's pretty high in salt anyway,
Yeah.
because of evaporation. All right, and we can only drink sodium chloride in water up to a certain concentration. Beyond that, it becomes pretty toxic. Okay, so you can drink salty water, but you know if you're going to try and drink seawater, within a few minutes you're probably going to vomit. It doesn't really go well. Okay. Yeah, or you start feeling sick, and that's what people, if they take on water when they're swimming, that's what causes them to be sick, because sodium levels go up in their blood, and it's not good.
So you can use silver nitrate to dissolve, to test for any chloride?
Yeah, I can use silver nitrate to test for chlorides in anything. I can test for chlorides in tap water. I could test for chlorides in urine samples. Okay, I could test for chloride in saliva, anything liquid. Okay, I could test for chloride using silver nitrate. Okay, not that I want to test for some of them, but there you go. But in theory, you could. All right, now, so what happens? Well, the sodium and the nitrate come together. That's a thing to consider because they're opposite charges. And the silver and the chloride come together because they're opposite charges. So it's normally the two inside ions with the two outside ions are the combinations that you want to look at. Okay, so we'll finish off the equation and it's going to look like this. So I'll keep it in a sequence, so that means I'm going to get silver chloride. Now, all chlorides are soluble except silver. So how do we show this as being a precipitate then? I might have shown you this earlier in the years. There's two ways you can do it. You can put an arrow down, which means it's solid. It's falling to the bottom of a solution. Okay? While we're on that topic, if an arrow goes up, what does that mean? It's normally a gas, it's bubbles given off. So an arrow down typically means a solid, although you can do this, Ag plus Cl minus solid. That would be exactly the same thing for us. And the other product is going to be NaNO3AQ, which doesn't do anything, it just dissolves, okay? Now, we haven't quite got there yet, because I was supposed to show you an ionic equation, and we know that this is a white precipitate, okay? So, just so that you are clear, and notice I've got the formulas, because sometimes we have to double to balance, okay, the number of moles. So you've got to make sure you've got the right formulas on the product side. Now, whenever we're doing a precipitation reaction, we only look at the stuff that forms a precipitate. Everything else disappears. So you have to do all that in the first instance, but really, this doesn't do anything, this doesn't do anything. We call them spectator ions. Because they're going to ultimately just be in the water, hanging around, looking at the silver chloride that's been produced. And they're just going to dissolve again. So they don't do anything in the reaction at all. That's what they're called spectators. So we get rid of that, and we get rid of that. So we get an ionic equation, and it looks like this. So our ionic equation would be Ag plus AQ. That's the only thing in silver nitrate that has reacted. Plus, over here, chloride. That's the only thing in the sodium chloride that's reacted, because all sodium salts are soluble. And if we keep on going, we just end up with AgCl. And that's our ionic equation. So the ionic equation only ever uses whatever ions form a precipitate. And that won't always be the case. Sometimes you might end up with soluble, 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 soluble.
So it's like silver chloride.
Yeah, silver chloride is a precipitate.
And it's white in colour.
And it's white in colour.
And that's why it goes cloudy.
That's why it goes cloudy. And we can use that as a qualitative method for testing for the presence of chloride in tap water. But as Alex said, I actually don't know whether it came from sodium chloride. It could have been potassium chloride, could have been ammonium chloride. So the chloride could have come from any other metallic salt. So I need to do another test to determine if it was sodium. And that is another test for quantitative, it's called a qualitative analysis, and that would be atomic absorption spectroscopy, which we don't do till year 12.
Yeah.
So you could do another test on it to see if sodium was present in the sample.
So if you wanted to find out sodium is present, then you could
Yeah.
test for ammonia. If that wasn't present, you could test for testing. There's no one test that does it all.
No, there's no one test that does it all. If you ever work in a lab, okay, in an analytical lab, then that's where the time is, because if you get a water sample, a teacher used to do this. So the state water laboratories are out at Bolivar, and so what they do is they go out on site. For example, they might go somewhere along the Torrens, and they'll bring in a water sample, okay, and they'll give it to the lab guy, and they'll say, okay, how much lead's in that? How much sodium's in that sample? All right, and they've got to do a test for lead, and they've got to do another test for sodium. They might ask, is there any amphetamines in the sample as well? They can test for, that's how they do it. They test the drain water for traces of narcotics. You can test those as well, okay? Not via a precipitation reaction, but they can test what's going down the drain and going out the Bolivar. That's where the time is, all right? So the stuff that you see on TV when they have that, CSI, and they take a sample of something in and they get the result within hours, that's rubbish, okay? It can take like weeks to test one sample, all right? Depending on the method that you're using to do the analysis, okay? Surinder.
So just when writing out the equations and stuff, do you always have to write a charge for in the beginning of the equation?
No, you don't have to write the charges because we've done stuff on like formula already. The only reason why I put the charges in was to sort of explain and show you that had this have been a different salt, I might have had to actually do some balancing of the equation in the front. That's all. Okay? All right. Any questions then? Because I'm not going to record all of it. I'm going to use it over here again in a minute. I just want to catch up. So this process over here, what do we call it in the book? They actually call it dissociation. I don't really like that word. It should be called solvation or ionisation, but we'll leave it as it is in the text anyway. So dissociation is taking a salt and dissolving it into water. What happens? Ion dipole bonds, that's how it dissolves. What does it look like? Water molecules surrounded by water. But you can only do that if it's a soluble salt. I had the example on the board a minute ago when I killed it. I said, okay, what about if I do it with calcium carbonate? Calcium carbonate is a solid. And if I look at my solubility table, all carbonates are insoluble. So if I react that with water, I'm going to get this. And I could say also there is no reaction at all. Okay? Didn't matter how much water I add, it's not going to dissolve. Okay? Because I can't break the calcium and the carbonate bond. It's too strong compared to a silver and a chloride bond. Alright, any questions on that one? I'm going to just later catch up on that, and then we'll come back to the second part, which is how do we actually use it in soaps and detergents.